Hi guys, my name is Kaylin Chapman. I am a Birmingham Southern College student. I am pursuing a degree with a major in biology and a minor in chemistry. Today we'll be discussing how to calculate Gibbs free energy. The objectives of today's video are to discuss the relationship of enthalpy and entropy with Gibbs free energy, to predict if a reaction will be spontaneous or non-spontaneous by the sign of delta G, to learn how the sign of enthalpy and entropy relate to temperature and how that impacts delta G, discuss the relationship between the equilibrium constant and Gibbs free energy, predict the sign of G based on the relative value of K, and to calculate the change in Gibbs free energy using either enthalpy and entropy or the equilibrium constant. The change in the free energy of a reaction is also known as the change in Gibbs free energy. Gibbs free energy can be calculated using either the change in entropy and enthalpy or by using the equilibrium constant. If you recall from the video, What is Thermodynamics?, we calculate Gibbs free energy to determine if a reaction is spontaneous, non-spontaneous, or at equilibrium. Some things to remember. If delta G is less than 0, the reaction is spontaneous. When delta G is greater than 0, the reaction is non-spontaneous. When delta G is equal to 0, the reaction is at equilibrium. As mentioned, there are two different ways to calculating Gibbs free energy. The first one we are going to discuss is using entropy and enthalpy. By measuring or calculating the change in enthalpy and entropy, we can predict whether a reaction will be spontaneous or non-spontaneous at certain temperatures. To get a calculated answer, we will use the Gibbs free energy equation. That is delta G equals delta H minus T delta S. Delta is that triangle, and that represents change. So delta G is the change in Gibbs free energy, which is energy available. Delta H is enthalpy change. T is temperature, and temperature will be measured in Kelvin. If it's measured in Celsius, all you have to do is add 273.15. Lastly is delta S, entropy change. This table lays out how to predict if a reaction is spontaneous or non-spontaneous at certain temperatures. In order to determine that, we will look at delta H, delta S, negative T delta S, and delta G. Before going into detail with each row, I would like you to take a look at column delta S and column negative T delta S. As you can see, these signs are always opposite. This is important for later on. In the first row, you can see a negative delta H and a positive delta S. As just discussed, since delta S is positive, negative T delta S is negative. All these factors contribute to a negative delta G, and that makes the reaction spontaneous at all temperatures. In the second row, you will see that non-spontaneous reactions at all temperatures are produced by a positive delta H, a negative delta S, and a positive delta G. Those first two descriptions are considered temperature-independent cases. That means that when delta H and delta S have opposite signs, the reactions occur spontaneously or non-spontaneously at all temperatures. The next two rows are reactions that are temperature-dependent cases, which means when delta H and delta S have the same sign, the relative magnitude of negative T delta S and delta H determines the sign of delta G. In these cases, the direction of the change in temperature is important. In the third row, delta H is positive and delta S is positive. With a positive delta H, the reaction will occur spontaneously only when negative T delta S becomes large enough to make delta G negative. This happens when the temperature rises. The last row shows when a reaction is spontaneous at lower temperatures and non-spontaneous at higher temperatures. Delta H is negative and delta S is negative. The reaction will be spontaneous when negative T delta S becomes smaller than delta H. This happens when the temperature drops. Steps to solving delta G. The first step is to convert all numbers to proper units. The proper units are kilojoules and Kelvin. Step 2. Plug all numbers into the equation and solve. The equation is delta G equals delta H minus T delta S. Step 3. Ask yourself, does this make sense? Does this match my prediction? Now let's go through an example problem to apply what we have learned. The question is the following reaction spontaneous? We know that we can determine if a reaction is spontaneous or non-spontaneous by the sign of delta G. And in order to determine the sign of delta G, we will look at delta H and delta S. Refer back to the table shown earlier and we can predict that the reaction will be spontaneous at high temperatures and non-spontaneous at low temperatures, since delta H and delta S are positive. Since this is a temperature-dependent case, we will have to solve the equation in order to determine the sign of delta G. Now remember the first step for solving for delta G. We have to convert all numbers into proper units. The proper units are kilojoules and Kelvin. We see that the change in enthalpy is already in kilojoules, but the change in entropy is not. To convert entropy from joules per Kelvin to kilojoules per Kelvin, we will be dividing by 1,000. As you can see, the joules cancel out, and then we are left with delta S equaling 0.3548 kilojoules per Kelvin. Now we have to change the temperature to Kelvin. So we have the temperature being 25 degrees Celsius, so we have to add 273.15, and now the temperature is 298.15 Kelvin. So the next step to solving this problem is to plug all the numbers into the equation. Remember, the equation is delta G equals delta H minus T delta S. With all the numbers plugged in, this is what it looks like. Now the first step is to multiply T times delta S, and that gets us 105.7. So as you see, now we have to subtract 105.7 from 119. That gives us delta G equaling 13.3 kilojoules. That means that the problem is non-spontaneous at 25 degrees Celsius. Does that match our prediction? Yes, the reaction is spontaneous at higher temperatures and non-spontaneous at lower temperatures. Now that we have gone over how to calculate Gibbs free energy using entropy and enthalpy, we will discuss how to calculate Gibbs free energy using the equilibrium constant K. This is also known as calculating standard free energy changes. This occurs when all components of the system are in their standard states. You can see that the equation is delta G naught equals negative RT ln of K. Delta G naught is the standard Gibbs free energy change. R is a constant that is 8.3144 joules per mole Kelvin. Temperature is T measured in Kelvin. Ln is the natural log, and we will take the ln of K, and K is the equilibrium constant. Delta G naught can be calculated, but it can also be predicted. Using this table, we can predict which direction the spontaneous reaction will occur. As you can see, the sign of delta G and K are the same for a given direction. If K and delta G are less than 0, the reaction is spontaneous to the right. If delta G and K are positive, the reaction is spontaneous to the left. If K equals 1, which means the natural log of K will be 0, delta G will also equal 0. Since delta G will be equal to 0, the reaction can be spontaneous to the left or to the right. Steps to solving delta G naught. The first step is to convert all numbers to proper units. The proper units are kilojoules and Kelvin. Step 2. Plug in the numbers to the equation and solve. The equation is delta G naught equals negative RT ln of K. Step 3 is ask yourself, does this make sense? Does this match my prediction? This time, we are going to do a slightly more difficult problem. For part A, we are going to find K, and for part B, we are going to find delta G naught. Part A says find K at 298 Kelvin for the following reaction. It gives us delta G naught at negative 36 kilojoules. For part B, it says use the equilibrium constant K to calculate delta G naught at 298 Kelvin for the following reaction, giving K to be 3.89 times 10 to the negative 34. The first step to solving this problem is to make sure all the numbers are in proper units. The proper units are kilojoules and Kelvin. As you can see, delta G naught is already measured in kilojoules and temperature is already measured in Kelvin. But as you know, the constant R is measured in joules, not kilojoules. So we're going to have to convert R into kilojoules. In order to do that, we're going to divide by 1,000. As you see, the joules cancel out and we are left with 0.008314 kilojoules. The next step is to use the equation and plug in the numbers. The equation is delta G naught equals negative RT ln of K. This is what it looks like with all the numbers plugged in. Since we are solving for K, we want to isolate ln of K. In order to do that, the first step is to multiply R times T. And there we get 2.48 kilojoules per mole. Now, we still want to isolate the ln of K, so we're going to divide both sides by 2.48. We are now left with negative 14.5 moles equals negative ln of K. So we can cancel out these negative signs, and then the 14.5 is now left positive. Now, in order to take the inverse of ln of K, we have to raise e to the 14.5 power. When we do that, we get the answer of K being 2.0 times 10 to the 6th. Now that is our answer for part A. Now we will move on to part B. The first step to solving this problem is to make sure everything is in the correct units. As you can see, everything is in the correct units, but we still need the constant R to be in kilojoules. Since we already have that math, I'm just going to pop that onto the screen. So we're using the same equation from the last problem, delta G naught equals negative RT ln of K. But this time we are solving for delta G naught. So we are given K, and we are given T, and we have R. So now all we have to do is plug that into the equation. That looks like this. So the first thing we are going to do is multiply R times T. As you can see, we get the same thing as last time, negative 2.48. And now you can see that ln of K is ln of 3.89 times 10 to the negative 34. So the next step is to solve for the ln of K, and we get negative 76.9. Now we are going to multiply that negative 76.9 times negative 2.48. And we get delta G naught equaling 191 kilojoules. That concludes this video. I hope that could answer some questions. Good luck!